Hello and welcome to my third lecture for the Brazilian ICPC Summer School of 2022. This lecture is going to be about hashing and more particularly about rolling hashes for string algorithms. However, towards the end, I will talk a bit about other uses of the hashing idea. So a basic question that you can ask in the context of string algorithms is why are brute force algorithms so slow? Now, the answer is very simple. Is basic operations such as comparison or determining whether some string is lexicographically smaller or greater than another string, these are very slow. So whenever you want to say, I don't know, I have a string A that is A0, A1, and so on, and it has n characters, so it goes up to n minus 1. I have some other string B, which is B0, B1, and so on, up to Bn minus 1, and I want to say A is equal to B. Well, if I want to know this, I have to compare each of the characters, first one, then the second one, and so on, until the last one. So this is On. Now comparisons, such as this one, are the basis with which we construct any algorithm. So it's essentially a problem that anything you want to do with strings will have an extra On factor that will make your life very miserable. Of course, the same is true for asking whether A is less than B or A is greater than B. So no matter what you try to do, you end up having to do a lot of On comparisons, and people have been designing very clever algorithms to perform as few comparisons as possible because these are very expensive. So there's a whole area of computer science dedicated to these kind of problems. But here we're going to take a different route, and we're going to try to deal with this On factor. So what's the basic idea? Well, when you compare numbers, let's say, this is very fast. So for numbers, comparisons telling whether a number is the same as another one is basically the definition of O1. For strings, we said we have On. Well, why don't we convert strings to numbers and then we just compare numbers? That means, formally, we take a mapping from the set of strings to a set of numbers, which I call h of s. These can be natural numbers, and if we make this mapping go both ways, every string is identified with a number, and this number is unique, then comparing the strings is just equivalent to compare numbers, and we are done. We transformed the On into O1, right? So the procedure would be, let's say you have string A and you have string B, you want to compare them, you first map them to some number h of A and h of B. You compare them here downstairs, where this is O1, instead of comparing up here, which would be On. So the rest of this lecture is all about understanding how to define this mapping. But defining a mapping from strings to numbers is not hard. In fact, we can define a perfect hash. And okay, this is going to be perfect in some sense and not very perfect in many other senses that we will discuss now. But ideally, what you would do is you have an alphabet. Let's say you have some possible characters that can be A, B, and so on until Z. Then to each character you associate a number. So for example, A goes to 0, B goes to 1, and so on, until you've assigned Z the number 25. In general, if your alphabet alpha has size k, you would assign B of alpha the set of numbers from 0 to k minus 1. Then, how do you define the hash function? Well, one way to do this is to just define h of a string A as the number that corresponds in base k to your string A. So this would be the first character, A0, but the value for it, as defined in the previous mapping, times the power k n minus 1, where n is the length of the string. The next character has value v of a1, and you would need to put the power of the base to n minus 2, continuing like this until for the last character, an, its value goes with k to the 0, which is 1. So, summarizing, we define the perfect hash by assigning a value to each character, and then for an alphabet alpha of size k, we consider the hash to be the number corresponding to the string in base k. So, for example, let's say you have the string ICPC, then the hash of this string is just the value of the character I times k, which I'll usually assume is 26 to the power cube, plus the value of c times 26 squared, plus the value of p times 26, plus the value of c again. So in this case we get something like 1, 4, 2, 3, 5, 2. And now that we have a number instead of a string, we can compare this number, 142,352, to some other number in O1. So, what are the properties of this hash function which make us call it perfect? Well, the first important property is that it preserves comparisons, right? So if you have a lexicographical order given by some comparison operator between characters, then you can say A is lexicographically smaller than B, and this would be an ON comparison where you check character by character from left to right, but this would be equivalent to comparing whether h of A is less as a number than h of B. So let me stress here, this is a comparison between strings, and this is a comparison between numbers. But I am saying that they are equivalent, so I should always compare numbers instead of strings, since it's much cheaper computationally. A different property that is related to this one is that it is biunivocal. That means that we have an equal operator that also translates from strings to hashes. So if A is equal to B, then h of A is equal to h of B. And moreover, if we have the right hand side, then A is equal to B. So if the hashes are the same, the strings are the same. Of course, another property that is very nice is it's simple to implement. This is just converting to a base k number, right? So it has a very simple implementation. However, this function also has some not so nice properties. In particular, these two are lost when you consider strings of different lengths. So if you're going to compare different lengths, you don't really know whether a string is equal to another string or not if their hashes are the same or one is less than the other. And a trivial example for that is that the hash of the single character A, which is 0, because the value that we assigned to the character A was 0, is also the hash to the string with two characters A, right? So now this property might be restored, but in particular this hash function, as we wrote it before, is not useful for that reason. Another bad property of this function is that it produces large values. In the example in the previous slide, I had a 4-letter string which gave me a number of order 10 to the 5. But if you consider lengths, for example 100, then in your hash you will have a factor 26 to the 100, which is sort of 10 to the 142. So a huge number that you cannot even represent in your computer unless you use arbitrary precision arithmetic. So these properties are pretty bad, and there's more. So in particular, evaluation of the hash, so computing it for the first time, is also order n, so we have not gained anything. If to compare two things, we have to first pre-process them, and this takes O(n) time. The question is then, do we give up, or do we try to fix the problems and we lose some advantages? What do we do? So as usual, the key point is you have to relax some constraints. So once you relax constraints, we'll see in a moment which ones we'll choose, then we gain flexibility. We don't have the constraints that we had before. We can be more flexible with the functions we consider, and then that means we will have more power. Of course, you know, with more power comes more responsibility. So, which constraint should we relax? We said we had a hash function that was mapping the set of strings biunivocally to the set of natural numbers. Now, the constraint I want to relax is this one. So the fact that the mapping can go back from the hashes to the strings. Let's consider what happens if you do not require this. Well, then in the hash function that we had, which was h of a equals the value of the first character times k to the n minus 1 plus second character k n minus 2 and so on until the last character an k to the 0. In this hash function, now we have freedom to choose v of a. We can replace the k to some other value, maybe not related to the alphabet. We can also add other kinds of operations. For example, if we want to keep the number small, we may take some modulo m at the end, and all this freedom will let us generate much more general hash functions than the simple base k representation that I considered before. So, summarizing, what did we gain? So, we have freedom to choose v of c, much more conveniently. We have freedom to choose a base which replaces k, and we have the freedom to choose a modulo m, at least in the simple modification I already presented in the previous slide. This will make you have small hashes in the range 0 to n minus 1, and these two things are just chosen for convenience. Then, what did we lose? Because you always lose some things when you want to gain some others. Well, one thing we lost forever, and there's no question, is comparison. So before we had h of a less than h of b implied, and this was on both sides, a less than b. Now that we are generalizing our hash function, we won't have this property anymore. Similarly, before we had that h of a would be equal to h of b if and only if a was equal to b. And again, this was very nice, but now we don't have it. The question is it the same how we lost irreversibly, let's say, comparisons to how we lost the comparison just for equality? So testing lexicographical order is much more than testing whether two strings are different. And I am going to argue that actually, even if our hash function is not perfect, it's not bionivocal, we cannot go back from the hashes to the strings, we can still compare hashes, and this will tell us something about the strings from which they come from. Now, it looks like things are pretty bad, because let's say you have L, the length of the string, large. This means you have many strings, right? But then, when you apply the hash function, you have some small modulo m, which means you have few hashes. And of course, if you have to put many strings into few boxes, each box is a hash, well, then many strings end up necessarily in the same box, right? They get the same hash. So these are called collisions. So hash collisions are instances of strings that are different, let's say A different than B, but you still have h of A equal h of B. And it looks like if you have a large number of strings and a small modulo, which gives you few hashes, which was something we wanted because we don't want large numbers, well, then you are bound to have many collisions. Of course, the hash function is easy to implement. It's still easy to implement, but can we use it for anything if it has many collisions? So let me argue how to deal with collisions, or moreover, how to not deal with collisions. Let's say, for concreteness, that you have L100. That means A is A0, A1, up to A99. Then, if the size of the alphabet is 26, let's say the English letters, what we have is, for the first character, here we have 26 possibilities, the same for the second one, and so on until the last. So, in total, the number of strings that we have to consider is 26 to the 100. This is the number of strings. The number of hashes is just m. Let's take m 2 to the 64. This is very convenient if you want to represent the hashes as unsigned long integers of 64 bits. Then the number of hashes, as I said, is 2 to the 64. If we divide these two numbers, we obtain the number of strings that have the same hash. This gives us 10 to the 122. It looks like we are completely doomed. There's 10 to the 122 strings for each of the hashes if we assume that they are uniformly distributed. Are we doomed? Actually, we are not, because you should notice that it's impossible to even consider this number of strings or this number of strings. In fact, when you have a problem in ICPC or like in any real situation, you will never consider all possible strings of a given length. You will actually consider some number n of strings, which will be, I don't know, typically maybe 10 to the 7. These may be substrings of a long string, or they may be many small strings, but in general, you will not have a huge number of strings because otherwise your input is already very large and there's no way to do anything with it. So if you have some given number of strings and you're going to perform comparisons between them, the most you can do is take the number of strings that you have, choose 2, so the binomial n factorial over 2 factorial n minus 2 factorial, and this is the maximum number of comparisons that you can do. So the real question you should be asking is, what is the probability that one of these comparisons is going to give you a collision? Well, to compute the probability of a collision, what you have to do is you take the number of comparisons and you say, for the first string I can get any hash, so I put a probability factor of 1, but for the second one I need to put the probability for the second hash to be equal to the first hash. If the hashes are uniformly distributed, this is 1 over m, the total number of hashes. And then this gives us n factorial over n minus 2 factorial times 1 over m, which for the values that we had before is approximately 10 to the minus 6. You should notice, however, that this probability for a collision is actually over this number of comparisons for n 10 to the 7, and this number is already huge. So it's not even possible to compare all these pairs. So in reality, you will be doing many fewer comparisons, and therefore the probability for you to find a collision is much, much less. But even assuming that it was 10 to the minus 6, what does this mean? It means that if there are, let's say, 1,000 test cases in the problem that you're trying to solve, then let's say the judges judge you 1,000 times, right? They run your program 1,000 times with 1,000 different inputs, and what they see is 999 times accepted, wrong answer, just 1. So, of course, no judge is going to run 1,000 times your program, they just run it once, twice. Then the most likely outcome is you'll get some accepted solution. So, what I'm trying to say is the probability of collision is much, much less than 1. Therefore, you can work as if, and this is technically not true, but you should assume that if the hashes are equal, then and only then the strings are equal. So while this is not technically true, it will be true in actual test cases because it's very unlikely you will have a collision. Now, this was the major issue that we needed to solve. Let me briefly comment on other issues that maybe are bugging you and I should clarify. First, the problem with the hashes always being 0. So what do we do if with our choice of the value for each character we get many hashes that are always 0? Well, one thing you can do is in your hash function for your string, you add one term that is a constant to the power number of characters in your string. And then you add the standard hash function that I have been using. So a0 base to the power n minus 1 plus the value of a1 power n minus 2 plus the other terms mod m. Now, whenever I need to, I use C5381, just because I like that number, but you can use your own, you can choose your own. As I said, for the base, there's not really any relation to the alphabet anymore, so you can use whatever you like. Normally, odd and more generally prime numbers are better, so I typically use P33 for small alphabets like the English alphabet. For the value function, I typically just take it to be what I said before, like the set 0 to k, the length of the alphabet minus 1, and I just let a be 0, b be 1, and so on. And these are just choices, but normally they work, and if they don't work, you can change them and you can use your own. Now, a major issue we had before was the computation time for our hash function. So it was on, and then we didn't gain anything if we can compare in O1, but to get the things that we need to compare, we have to spend on time. Well, in this case, there is a trick that usually works, because normally we don't have a lot of different strings to process. We just have a large string, and we need to process some substrings. So if this is our A from 0 to n, we may be interested in computing the hash for some substring from A to B. The key observation here is that the hash of the string from 0 to A is essentially the value at position 0 times the base to the power A minus 1 plus the value at position 1 times the base A minus 2, and so on until the value at position A minus 1 times the base to the power 0. Of course, we have some mod operation, but I'm not writing it because we know everything works through the mod operation. Now, the hash of the string from 0 to B is something similar. It's the value at position 0, but now you have the base to the B minus 1 plus the value at position 1 times the base B minus 2, and so on until the value at position B minus 1 times B to the 0. So in red, I have the hash up to here. In blue, I have the hash up to there. And if we can do blue minus red, we get this thing in green would be the hash from A to B, which is what we want to find. So let's look more closely at the hash from 0 to B. I said we had B0, the base, to B minus 1, but then after some terms we get the value at position A minus 1 times the base to the power B minus 1 minus A minus 1. And you should notice B minus 1 minus A minus 1 is just B minus A. Then of course you have more terms, so the next one is the value at position A times the base to the power B minus A minus 1, and then you have many more until you reach the last one, which is the value at position B minus 1 times the power 0 of the base. Now you should see that the hash of the string from A to B is nothing else than the value at position A to the power B minus A minus 1 plus, and so on until the value at position B minus 1 base to the 0. So it's essentially this part that we have as the second part of the hash from 0 to B. Meanwhile, the first part that we had here is related to the hash from 0 to A, but we had this extra factor of the base to the power b minus a. So the final result is that the hash of a from small a to b is nothing else than the hash of the string from 0 to b minus the base to the power b minus a times the hash of the string from 0 to a. So in code, we first pre-compute all the powers of the base. Here, we do this just once in the beginning of our code. Then, when we have a string, we compute all the hashes of the prefixes. So that means h of I here computes the hash of the string from 0 to I. And then we can use this to quickly calculate hashes of any substring. To do this, we just directly implement this function where we use the powers that we have computed before and the hashes of the prefixes that we also have pre-computed. So you should see here that the pre-computation is on, and then each substring is hashed in O1, and I'm avoiding everywhere the mod m because I'm assuming m is 2 to the 64 and I store hashes in unsigned integers, so this operation is done for free without me having to specify it. So let's discuss some examples. The first one I want to talk about is repeated substrings. So let's say I have a long string and I want to see which of its substrings are repeated. Maybe I want to see the maximum number of repetitions or the number of substrings that are repeated at least k times, these kind of things. Naively, you would first go over the lengths of the substrings, which can be 1, 2, up to n. Then you would go over the positions. Let's say I, they can go from 0, 1, and this would go up to n minus l. These would be the positions where the substring starts. The first step gives you a factor on, the second step gives you a factor on, and the third step would be to use a map or some other structure to count repetitions. Normally, this would be O, n for the comparisons to put things in the map, and log n for the usual factor of the map running time. But now we have converted this to just O log n. So our final running time of O n square log n is much better than the on cube log n that we would otherwise have. Another example that we can consider involves palindromes. So palindromes are strings that are read the same going forwards or backwards, right? Like, for example, A, B, B, A. To check for palindromes in a large string, what you need to do is keep two different hash functions. One goes from the start of the string towards the end, and I will call it h direct. But now we also do another hash function, h reverse, which is the same function, only you start processing at the end of the string, the last character, and then you start adding characters one by one in this direction. Whereas originally we were starting at the beginning and adding characters in this direction. Now, if you want to check that a substring, let's say from A to B, is a palindrome, you need to check that h in the direct sense from A to the middle, which is A plus B minus A over 2, is the same as H in the reverse direction from the middle of the string, A plus B minus A over 2 up to B. So if these two hashes coincide, then the part of the string that is on the first half coincides with the part of the string that is on the second half when you reverse it, and this is exactly the definition of a palindrome. Of course, I am being a bit sloppy here about the indices and whether the string has even or odd length, but you can figure those out yourself pretty easily. And in the end, in many cases where you have problems dealing with palindromes, all you need to do is have a quick way to test whether a substring is a palindrome. With this condition, you can just write a simple function that checks in O1 whether a substring is a palindrome or not. So this is all very nice, but can we do something better? Now, I said before that we lost comparison. So for now, we are always dealing with just telling whether two strings are the same or not. But can we recover the comparison between strings? Can we now say, using hashing, whether A is less than B or not? Let's say you have a string A, and let's say you have a string B. Then, to compare A and B, we need to find all the characters for which A and B are the same and identify the next one. So the next character is the only one that will define whether A is greater or smaller than B. So how can we find this length of characters where they are the same? We can just binary search. So we can just test whether A from 0 to some length L is hashed to the same value as B from 0 to L. And then, if this is true, we should increase L, and if this is false, we should decrease L. But when we finish our binary search, we will know the maximum length that these two strings have coinciding in their prefix, and the next character that we look at will tell us about how the strings compare. Because we used binary search, the comparison is now O log n, which is again much better than On, the naive comparison. In code, comparing two suffixes of the same string, starting at A and B, is very simple. We binary search on S the number of characters that coincide. Then, once we have found this number, we have to compare the string at position A plus S with the string at position B plus S. So, the binary search trick to speed up comparisons will give us a lot of options to implement naively things that were otherwise very hard. For example, using this comparison, we can very easily code in just 2 lines the suffix array for a string. Remember, the suffix array was just an array that contains the indices for the suffixes of the string in lexicographical order. For example, if you have a string such as this one, banana, then ordering the suffixes, you have A, N, A, N, A, N, A, B, A, N, A, N, A, and so on. And you can see that this one starts at 0, 1, 2, 3, 4, 5. So the suffix array would contain 5, 3, 1, 0, and so on. So there's many efficient algorithms that are quite elaborate to construct suffix arrays, but this one is O n log square n, because we have to sort, which is n log n, and our comparison function includes a log n factor, and it's just 2 lines, and it's not much worse than n log n, which is what you would normally get with a simple implementation of the suffix array. So it's pretty good, and it's very simple. You can also take things even further. So I'm just going to briefly mention this, but what about making things dynamic? So for now, what I have been talking about is just having a static string, hashing it, preprocessing it, and then using those hashes in your algorithm. But you can have dynamic hashes, and for example, in the problem Jupyter attacks from, what was it, 2011, Latin American regional contest, you basically had to implement something that was a data structure computing hashes. But this structure was required to do 2 things. First, compute hashes, let's say h of a substring a, b. In this problem was required log n, or you could also do O square root of n if you were not too sloppy when you programmed it. So this is the standard thing which I've been talking about, but the non-standard thing was it also should allow you to change the underlying string in an arbitrary position, and this was also required to work in O log n or O square root of n. So you see, computing hashes would no longer be order 1 but log n, and this would add a log n factor to all your running times. But the upside is you are now allowed to change the underlying string also in O log n, and you can still compute hashes and everything is updated immediately. So I encourage you to go to this problem and look at it, maybe try to solve it. This is good practice, and also it's a nice tool to have when you have some dynamic string problems. So you see, hashing is very powerful. It allows you to turn comparisons from On to O log n, and this opens a whole world of possibilities. However, I should mention, everything we said today is not correct. So technically, all these solutions and all these algorithms that I presented give you wrong answers. I argued that in practice, the probability of you getting a wrong answer is very small. But of course, this is only true if you don't get caught. In particular, if someone can read your code, you have a problem, because they may have the ability to prepare test cases precisely to destroy your hashing function. Now, one way to avoid getting caught, so how to avoid problems with your hash function. One way to avoid this, especially, for example, in online competitions where people try to hack your solutions, is to not choose the constants. So, for example, I said B33 may be a good choice, but someone can create a special test case that breaks your hash function with B33. Then you replace that by just taking B from a set. I don't know, take 33, 37, 41. And, choose randomly at runtime from this set of bases. Then, if someone tries to hack you with a case that is going to make you have a collision for the base 33, maybe you will get at runtime to choose the base 37. It's very, very unlikely that this case will also be problematic for that base, and their hack won't work. You can go even further, for example, randomizing the choice of V of C. So if you take this, you can still, for example, take V of the alphabet to be just the numbers from 0 to the number of elements that you have, but for example, you can shuffle them. Then, if someone prepared the test case assuming that A was 0, B was 1, because you have shuffled, A will be some other number with high probability, and this hack will also not work. So if someone is going to read your code and try to break it, you can make it so that your code does not show the information or is not deterministic about the hash function that it chooses, and therefore this will break a lot of attempts at hacking your code. However, you should still be careful about test cases that produce collisions very generally, for example for any base or for any choice of assignment of values to the alphabet's characters. I want to now tell you about a particular test case that can be used to break the hashing algorithm that I presented for the specific modulo 2 to the power 64. So the hack is based on a recursive definition of a string sk, which I will take to be the string sk minus 1 concatenated with the string sk minus 1 bar, where the string sk bar is just the string sk with the characters a and b interchanged, and I only have to give you the initial condition, which is s0 is just the string a. So in this way, you see, to create a string at the next order, you need to concatenate the string in the previous order and its complement. So for example, s1 is just a from s0 and the complement of a, which is b. Then s2 is the previous one, ab, and the complement of that, which is ba, and so on. So this string has length lk, which is clearly 2 to the power k. So for k0 it has length 1, for k1 it has length 2, and so on. So let us now compute the hash of sk. With our hashing function, we have that this is the hash for sk minus 1 times the base to the length k minus 1 plus the hash of the string k minus 1 complement. The same is almost true for the hash of the complement. This is the hash of the first part when you complement times the base to the length of the string k minus 1 plus the hash of the string sk minus 1. So if you define decay as the difference between these hashes, so h sk minus h s bar k, then this is simply this term and this term times the base to the power lk minus 1, so h of s k minus 1 minus h of s bar k minus 1, and then you have this term and this term, which give you minus, again, h sk minus 1 minus h sk minus 1 bar. So, because this term and this term are the same and they are just equal to dk minus 1, what we have as the end result is dk minus 1 times b to the power lk minus 1 minus 1. So we have found a recursion for decay, the difference of the hash of sk and the hash of sk bar, and what we are wondering is how does this evaluate mod r power 264. So we have to check how many factors of 2 there are in decay. As you may be already guessing, if we find that there are more than 64 factors of 2 in some decay, then this evaluates to 0, and we have found a collision between two hashes, the hash of sk and the hash of sk bar. So let's proceed. We said we found that decay is dk minus 1 times b to the power lk minus 1 minus 1. And we also had, from before, lk is 2 to the k. So let's start counting powers of 2 in this expression. So we have b lk minus 1 minus 1. We can write it as b lk minus 2 squared, because 2 times lk minus 2 is lk minus 1 squared, because 1 squared is 1. And this is a difference of squares, so I can write it as b lk minus 2 minus 1 times b lk minus 2 plus 1. Then, repeating this process, because now we have again this term, which is the same one with k minus 2, we have that at the end we will get b lk minus 2 plus 1 left from the first difference of squares. The next difference of squares will give us b lk minus 3 plus 1, and this will continue until we reach b square minus 1, which itself is b minus 1 times b plus 1. Now, because b is odd, the base should be odd, because otherwise powers of the base will already have large powers of 2, and our whole hash won't work. So because b is odd, this term is even, this term is even, and so on for each term in this product, which then means that we have here at least, probably more, but we have at least a power of 2 to the k minus 1, if you just count the number of factors that we have in this product. So now let's analyze what happens with decay, for which we have this recursion. Defining dk with small d as the number of factors of 2 that we know divide dk, we have that this is dk minus 1, because we had that term in the recursion, plus the number of factors of 2 that come from b lk minus 1 minus 1, which we just saw was k minus 1. So this is a very simple recursion. It just tells you that dk is the sum from I0 to k minus 1 of I, which is nothing else than k times k minus 1 over 2, and importantly, this grows very fast. This is OK squared. Then we have proved that 2 to the power k times k minus 1 over 2 divides dk, which was the difference between the hashes of sk and of sk bar. But consider, for example, the case when k is 12. So 12 over 2 is 6, and 6 times 11 is 66. Then this factor is already larger than 64. That means that this difference here evaluates to 0 mod 2 to the 64. Therefore, we have found the collision in our hash function, and this collision is completely independent of the base. We just assumed the base was an odd number, and it's also independent of the assignment of values for characters. So it was unimportant which value got assigned A and which value got assigned B. Now, this is pretty bad because we said K12 was already giving us collisions, and this gives us L12, which is 4096, which is not a very long string. And if we have a very long string, let's say like K equal to 20, which would give us something that L20 order 1 million, then S20 contains many copies, just because how we defined it. It contains many copies of both S12 and also S12 bar. So this is pretty bad. Now, in some problems, these strings are not a possible input. So maybe the string has to satisfy some properties, and then you cannot just pass these strings that are carefully crafted as some input for your problem. But for those problems where this test case can be included, you definitely have a problem if you use modulo 2 to the 64. So the solution here is to change the modulo. So the only thing that you can do is change m. So before we used m 2 to the 64 simply because it was automatically implemented by unsigned long operations, and we didn't have to actually write the modulo operation. But you can always just choose m equal to some prime p large, right, close to maybe 2 to the 64, but not precisely that one, and this completely breaks this hack. So this hack is only working for the particular modulo 2 to the 64. It will not work for any other modulo that is not a power of 2, and then we are saved. So of course, taking mod p with p sum prime in each hash operation is annoying. This will make your code slower. So the takeaway here is be careful if someone is going to prepare bad inputs for your program, and in particular if those inputs can be carefully crafted like the strings we just presented. You have to be very careful about the choice of constants that you use in your hashing function. So this concludes what I wanted to say about hashing for strings. I will now just very briefly mention about set hashing. So I just want to stress that the idea of hashing is much more general. It doesn't really apply only to strings, and it's very powerful. So consider, for example, the following problem. Let's say you have some elements. So the elements can be, for simplicity, numbers. I will take 0, 1, up to n minus 1. So you have n numbers, and you have some sets. Let's call them A, B, and so on. So the problem is to provide some data structure that can do the following. It can add an element to a set. So you tell me an element and you tell me a set, and I can add that element to that set. It can remove that element from a set if it is there, and it can tell me or answer questions about the sets. So the type of questions that we can ask are, for example, what is the most frequent set? Let's say we have k sets here, and which one is the most frequent, or how many repetitions are in this set of sets, and so on. So can you provide a data structure that can do all these things? Well, of course, the naive thing is to just use a simple data structure and compare sets by just taking all the elements, maybe sorted. So here comparison would be n log n. Of course, you can try to think about more complicated data structures that would solve this problem, but what I'm trying to show you is that you can actually use the simple data structure and just compare in O1 using hashing, just like we did with strings, which will make everything much faster. Now, if n is small, it's not hard to think about such a data structure. Basically, you can assign the element, let's say I, you assign the value 2 to the I. So this represents elements, and to represent a set, what you do is that if you have a set, for example 3, 4, you represent it with a binary number that has ones in the positions of the elements that are there. So this set would be 1, 1, 0, 0, which is 2 to the 3 plus 2 to the 4, and that is 8 plus 16, 24. So this is the representation for sets. And in fact, the operation that I'm using here, I rather not represent it as a plus, but as a XOR, right? So here they are the same because these two numbers don't share any bits. But for what follows, it's going to be better to think of this operation as XOR. Then, how can we add things to a set A? We just, let's say, add I to A means take A goes to A XOR 2 to the I. Removing I from A is just, again, taking A goes to A XOR 2 to the I. Because if we had added it, this bit was on, and then when we remove it, we just turn it off. Then, checking or answering questions about the sets is very easy, because for each set you have one number, and you can compare these numbers, you can count them, you can keep them in a data structure of your choice to keep them ordered, and so on. Okay, that is good, but that only works for n small. What about n large? In particular, if you have more than 64, you will have trouble implementing these bitwise operations directly in, I don't know, unsigned integers. So what do? Well, before we said we assigned some value to a specific element. Now we are going to generalize that, and instead of assigning 2 to the I to some element, we assign a random value to this element. We will assign a random number, let's say in the range from 0 to 2 to the 64. This range is just 64-bit value. So you see, the random value that we choose is nothing else than a hash for the element. Then, if a set A contains elements A1, A2, and so on, it is assigned a hash, and this hash is nothing else but the hash of A1 XOR the hash of A2 XOR until the end. Then each set is represented by a number, a hash of its elements, and the question that we have to ask is, if we have two sets, say A and B, and we see that the hash of A is equal to the hash of B, so we see a collision, is this really a collision, or is this related to the fact that A is the same as B? If we can state that with high probability we have that A is equal to B, then this is a good hashing function, collisions are improbable, and we can just use these hashes instead of the full sets. So let's then compute the probability of a collision in this scenario. we said we have A and B. For there to be a collision, we need to have A different than B, yet the hash of A equal to the hash of B. But the hashes were just the XOR of the different elements that each set had. So this is hash of A1 XOR hash of A2 XOR and so on should be equal to the hash of B1 XOR the hash of B2 XOR and so on. And because we can XOR with the same values on the left and on the right, we can assume, without loss of any generality, that on the left we don't have any repeated elements with respect to the right. But then, for each bit here in the left, what we see is that it has a random probability of being 0 and 1. Remember, we just chose the hashes of each element randomly, so it was a uniform distribution over all the 64-bit values. When you XOR that with another uniform distribution, you still get a uniform distribution. So here each bit has 1/2 probability of being 0 and 1, so this is uniformly distributed over 64-bit values. And the same is true on the right. So this is again uniform distribution over 64-bit values. Then, for there to be a collision, no matter what the hash is on the left, so the probability of a collision has the probability of the hash on the left being something, which is just 1, times the probability of the hash on the right to be exactly the same thing, which is 1 over 2 to the 64, and then this is just 2 to the minus 64. So the probability of a collision is very, very small. From here on, the computation goes exactly like what we did for the strings. You can have many sets. We said we had k, and you may want to compare all of them to all of them, so you have k choose 2, and to compute the expected number of collisions, you should include the probability 1 over 2 to the 64, and this is still very small, because you will never be given so many sets that k choose 2 is much larger or at even the same order as 2 to the 64. So the conclusion is, again, the expected number of collisions that you have is very small. Therefore, you can use this hash as if it had no collisions, and your data structure to work with sets and count how many different sets you have and things like this is perfectly fine for most applications. So we have reached the end of this lecture. I hope that you learned something about hashing today, and that you will try to use it in practice if you are not used to it. I just like to point out that the hashes that I presented for the strings and for the sets are actually very similar. The main difference is that for strings, it's important to have an order, right? So the order of the characters is important. For sets, it's important to not have an order. So you want to either know whether the element is there or not. And for other types of objects that you want to define hash functions, you just have to find a suitable operation and hash function. So operation for your hash function. So once you find a suitable operation that respects the properties that you want your objects to have, it's not so hard to define a hash function that has low collision probability, and then you can use these ideas to speed up all your naive algorithms. So with this, please ask questions if you have them, and see you in the next lecture.